Voltaic cells.
Is this where
By the way, you have this paper, okay? The one that you did the electroplating on here today, get that out in front of you. You're going to need this. And I want you to add a little something onto it because there's something that I forgot to put there. All right? You all have that in front of you?
No. Yeah.
Underneath Roman numeral 4, electroplating, right? This should be above the A for this one. It should be Roman numeral 5. Or, yeah, it should be 5. Or do we, no, we have something in between there or no?
I don't think so. No.
Oh, that's right. Yeah, I'm reading it backwards. This is Roman numeral 6.
Yeah.
This is Roman numeral 7. So for Roman numeral 7, voltaic cells there, and then write C notes because I have about a half a page of notes to give you. You'll have to do in your notebook. I only put this picture on here so you didn't have to draw the whole picture out. It just takes too much time. Okay, so just write down above A, voltaic cells, write down 7, above A, zinc copper cell, write down 7 voltaic cells. And then put C notes, because these are the notes you're going to put. You're going to put these notes in your actual notebook. So get your notebook open to be able to do this.
We have a binder. We don't have a
Your binder. All right? Now, what's a voltaic cell? Well, a voltaic cell uses spontaneous redox reactions to produce electricity. We're not talking about the electrolytic cells we've been doing up till now. Both the electroplating and the electrolytic cells we saw before. There were several different kinds. There was, the sodium sulfate cell, the sodium chloride cell, okay? And in some cases, we would have observations. We would say, chlorine gas is produced, oxygen gas is produced, sodium metals produced. It becomes basic here. It becomes acidic here. All right, all those things you have for that kind of a cell, we're using a battery. You would hook a battery. I used that thing over there both times for both the electroplating and the one back there. I used a battery to force a current to make a reaction happen that shouldn't happen. Here, I take spontaneous reactions that want to happen, and I have them generate electricity. This, another name for a voltaic cell is?
battery.
A battery, yeah. It's just a battery, okay? Now, the thing about a battery is, you don't realize this because it looks like it's all one piece. Look, it's all together. It really isn't, all right? It really are two parts to a battery, just like there are two parts to this, okay? And I'm going to illustrate this with you. Hold on a second. I got to get this a little bit higher so people can see it.
I'll get higher.
Yeah, if you go to Costa Rica, you can get. No. All right, there. This is my 2-potato clock. Okay, let me explain what's going on here. All right, you may remember seeing this. Maybe if you had me a couple years ago, you probably forgot we even did it because it was the first week of school, and I was simply trying to show you all the evidence of the chemical change. One of them would be generating electricity. Okay. There's a chemical change going on here, and at the time I used bananas, I believe. It's that earlier this year. Maybe I did last year too. But you can use anything that will conduct a current. All right, and people were asking like, well, how do the bananas or how do the potatoes, make what, as you're going to see, electricity? All right. Well, they don't. It's not the bananas or the potatoes that make electricity. It's these two wires made of copper. This guy's made of copper. And this guy's made of zinc. Now, if I just touch copper to zinc, they'll react. If I let them sit there, I come back, they're going to corrode. They're going to redox each other, oxidation and reduction to each other. But if I separate them out and make those electrons that would have been transferred flow through something and do some work for me, it's kind of like water going past a water wheel on a mill, okay? If you think about it. All right, the water. If I put a water wheel in a lake, nothing's going to happen. If I put a water wheel on a stream, we have different heights of water, and the water is going to flow past it. It can make work go. So, here's water in a lake. The two guys are already touching. They're right there together. They're just going to react. But if I separate them out and I make the electrons flow through something like a clock or a light bulb, I can get work out of it like I can get work out of a water wheel. All right, that's the whole idea behind a voltaic cell. I'm going to come back to this in a second. The oxidation and reduction reactions have to be physically separate in order to set up a potential difference or a voltage. But they have to be electrically connected as well to complete the circuit. And I'll talk about how we do that as well. That's something called the salt bridge. There are two parts to this. Okay? Now, when you take, by the way, I don't know if you only one person in here, Jesse, you've had physics A&M. Does he use water as an analogy? Good. Then you'll understand all that I'm about to say. I have not done this with you guys yet, but I'm going to show you a little bit of my analogy to water and electricity. It is not perfect by any means, but it definitely illustrates the point. Let me show you. You don't have to draw this. Actually, it's on the back of this paper. Okay? So on the back of this paper is everything I'm going to say and more. Okay? All right, about water. Take a look. See, I've got a waterfall. This is a short waterfall. Here's a tall waterfall. Which one can I get more power out of? Which one can I get more energy out of? Yeah, the water's got to fall a greater distance. There's a greater potential difference between their heights, greater potential energy there. Okay? Well, that's analogous to your batteries. Okay, I could have, and by the way, you won't know until Monday how we determine that difference. But basically, we're going to see about the standard reduction potential. We'll look them up in a chart and see how much this guy wants to be oxidized or how much this guy wants to be reduced or whatever. All right, you could actually, there's actually numbers based on it, a standard electrode. All right, so that's the height of the waterfall. The difference is the voltage. Okay, that's how. Now, what do you think the flow of the water is analogous to? As it flows past something.
The flow through the batteries.
Right, flow of what?
Electrons.
Yeah, which was called what? The
Voltage.
No, the voltage is the difference in height. What's the flow going to be? He knows it. What's everybody else? Come on, think.
Right, the current.
The current, sure. The current. Matter of fact, here, let me, I actually have this picture right here. All right, I'll go to this one. It'll be a little bit easier. All right, so basically, your voltage is the water pressure you have. All right, it's the potential difference between 2 points. The greater the difference, the more energy you're going to get out of it. Okay, the work as the water flows past a point, in this case a water wheel. If I take a look over here, all right, as the water flows past the water wheel, all right, it will. If I had higher and it had more force, it would be able to turn that water wheel faster. All right, and here it's going to be the battery. What voltage batteries? 9-volt batteries, whatever. Okay, that's the work. As the water drops from a higher level to a lower level, it can do work. As the voltage drops from a higher potential energy to a lower potential, it will do work. The current, flow of electrons, flow of water, right? Now, this is something we do not deal with, resistance, but this is something I'm sure Schrader talked about. Resistance would have to do with how big the pipe is. All right, more water could flow through a larger pipe. Smaller pipe, going to be greater resistance, okay? All right, so that's basically your analogy. Now, what does that have to do with my cell here? That's what I'm going to get back to right now. Well, in order for this to work, I can't have these guys together. I've got to have them at different heights. And that's why I've got separate cells. There are actually 2 cells here. One called, well, they're actually called half cells. All right? I have to physically separate it. Check it out. I just said a minute ago, copper, turn the light on for a second. You probably see it better on the camera. Copper wants to get together with zinc. If I put those 2 guys together, their electrons will be transferred. But they'll be transferred directly. But here's what I'm going to do. I'm going to separate these guys. This is my zinc electrode, and here's my copper electrode. All right? Here's my copper electrode. Here's a zinc electrode. Watch what happens when I put this guy into the potato. Watch what happens to the clock. What happened?
No way.
Yeah, it turned on. All right, the clock is now on. It's working. Why? Because the electrons want to go from basically, I'm trying to think which way. I don't want to get it wrong. They can flow from one guy through here into the other one. I'm going to diagram it better for the actual cell. All right, but they're separated right now. If I were to touch them, it's not going to work. All right, it has to be separated electrically by the potatoes. They're just a conduit with ions. All right, so if the zinc is becoming +2, he's going to zinc metal. So that means he's using electrons. They must be getting them from the No, I mean the copper's getting them from the zinc. It doesn't matter.
It doesn't matter.
When I diagram on the real cell, it'll be more obvious. But the point is, this works because they're separated, and I make them go through here to complete the circuit. Okay. All right. If I just touch the copper to the zinc, it ain't gonna work. All right, because there's just gonna be it's like water at the same level. All right. I have to have water separated somehow, and the way we separate them, turn that light off, is through things called half cells. All right. So you'll have the oxidation and the reduction are basically both forms of it are in each cell, but they're separated. They contain the oxidized and reduced forms of each element for the zinc ions and zinc metal, copper ions and copper metal. All right, and you need to write these down. Okay, that's your half cell. That's the separate part. That keeps them separate, keeps them from a different potential voltage. The way to connect them together is through the salt bridge. The salt bridge allows in this case, it's just basically, well, you're going to make it two different ways. In this case, it's just a potato. The salt bridge allows them to be connected electrically. The ions will be able to flow without actually touching. Because if they touch, they're just going to be, reacting and oxidize and reduce each other directly. I've got to have the water at a different level then. As it flows past, so it will flow past something that will work. Okay.
Now, how long will that run for?
Well, I'm going to show you in a minute. I don't know how long, but it will eventually, you're right, run out. Batteries, as you'll see in a minute, they don't last forever, and you'll see why they don't last forever.
What about potatoes?
See, again, I'm going to make this clear to you. In Chem 1, you guys probably thought it was the potatoes giving it the energy. It's not. The potatoes are just the salt bridge, and I'll show you what that salt bridge is when I diagram the cell in a second. The energy is coming from the fact that copper wants to react with zinc. And so I've just physically separated them and made them get their electrons flow through something to get to zinc.
So the potatoes are just a connector?
They're just a connecting. Yeah, it's a way to connect them together. I use bananas. I could use an orange. I could use anything. I could use salt water. I could use anything.
Could you use bulk?
I could not use bulk.
You have to stab.
I'm pretty salty.
He's not. Yeah, he is salty. Okay. Now you see this picture on your paper. You're back to the paper now. We're going to fill in the stuff on the paper. All right. Now, if you look at this picture on the paper, we need to fill everything in here. Okay? You watching?
Yeah.
Like the electrolytic cells. I'm going to give you observations in these homework for tonight. By the way, you're going to be able to predict some of these observations after Monday. And then we're going to make the stuff probably on Tuesday. We're going to actually do a lab on it on Tuesday. All right? The observations will look something like this. First of all and foremost, you actually notice you have 3 observations here. Does it have 3 on there? Okay, it has 3 on there for a reason. The first one has nothing to do with the electrodes. It simply says this: an electric current is produced and maintained. In electrolytic cells, that is not the case. What did I have to do with an electrolytic cell when I wanted to decompose water or copper plate that spoon? What did I have to do? I had to pass. I had to pass a current. I had to put a battery, or in this case a voltage generator, up to that solution or whatever it was to make a non-spontaneous reaction happen. Here, I just hook it all up and bam, I've got electricity. It's generating electricity. Okay, that's number 1. Number 2, notice there are 2 separate things here. You got to draw these differently. You don't have one jar where everything's in it like you had with the electrolytic cell. Here you've got 2 separate ones, and that's your salt bridge, by the way. Okay, so that one of these, in the copper one, I'll notice that the copper electrode's getting bigger, and I'm losing copper ions. That blue color will get less and less and less over time, and the copper electrode will get fatter and fatter over time. The blue color comes from the copper ions. You've seen copper sulfate solution, copper nitrate solution. This is what we use to do. We use this solution here to do the electroplating the other day. It's blue.
It's Gatorade.
If I let that stuff go here for a very long time, I'll notice the blue color get less and less and less and less, and the copper will get bigger and bigger and bigger. Okay? Zinc, on the other hand, zinc electrode is decreasing. I'm going to get less and less and less zinc and more zinc ions. in the solution. Okay? Now, zinc doesn't really have a color, so you won't notice the ions. And actually, you won't even notice a difference in color for the copper because we're not going to let the batteries run for that long. I don't think you have labeled on yours, and you should. This is the salt bridge. Right there. That's the salt bridge. And I want to diagram what's happening with those electrons as we go along here and what exactly is going on here. Now, underneath here, you're going to fill these things in. Now, honestly, I'm looking at your paper, and it looks to me like you don't have room underneath. You're going to have to do it to the sides here, right? You probably have more room on the sides. All right, that's what we'll do. All right. Now, here's what you're going to do. We're going to look at the reactions down below in a second. But before, we're going to fill those in. You can fill those in as we do them. But I want you to get used to being able to just write them on the side, kind of like you did with the electrolytic cell. So let's just write them there. What's happening at the copper electrode? All that's happening here, it tells me the copper electrode is increasing and the ions are decreasing. So that means, wouldn't you all agree that what must look like this? Cu with a +2 must be becoming Cu metal, right? Because the electrode for the copper is getting bigger and the ion concentration is getting smaller. In order to do that, what's it going to take? 2 electrons. Okay. All right. I guess it's already labeled here, but when something is, not everything's labeled here. When this guy's absorbing, accepting electrons, what do we call that? That's reduction. And it's already labeled that anywhere the reduction happens is called the what? The cathode. So that's already there, cathode. Okay. I didn't erase that from your thing, did I? Because I did try to cover up most of the stuff on there. Now, what's happening at the zinc side? Well, the zinc electrode is decreasing, so I'm taking Zn metal, and it's becoming Zn with a +2 charge. And in order for that to happen, what must be happening with electrons? Isn't he giving off 2, right? Make sense? Is that oxidation or reduction? Oxidation. And that makes him the anode. Everybody good with that? All right, so far so good. That's pretty easy to do. By the way, when it talks about reactions, you could write those down in there if you wanted to, but you really don't have to because if you've got them up here, that's where I really want you to diagram them anyway. Now, it's time to look at what's going on here, and well, the one last thing that's confusing about it. So first of all, what's going on? Let's trace the electrons. Let's find out what's happening here. All right, zinc is going from zinc metal to zinc ions. So we're going to get less and less of this zinc metal. And it gives off the 2 electrons, which do what? Those 2 electrons travel up the wire, okay, through the voltmeter, okay, and down to this side. What happens, what do those electrons do when they get there? They are accepted by copper, right, and become copper metal. Now, meanwhile, these negative nitrate ions are going to basically be forced the opposite way, away from that one, and continue the charge. No electrons are transferring now, but the charge, all right, goes back over here, all right, and we'll push those zinc metal and zinc ions together too. So, actually, yeah, the zinc ions would be going this way. All right?
How does it get like this through the salt bridge?
Well, again, it's just pushing. These positive ions are going to push negative ones that way, and negative ions are going to push positive ones that way.
Okay.
All right, because the salt bridge is merely a solution of. I have to erase all this. Well, no, I don't. I can erase just that. The salt bridge is a solution, in this case, of sodium nitrate. I'm going to use ammonium nitrate, ammonium chloride, I think, for my salt bridge when I make it. So they're basically, and how we're going to make the salt bridge, we're just going to have a cotton and a saturated solution of some ion that will not react. See, you say, well, why don't I connect it with a wire? Why wouldn't I connect these with just a wire? Well, because copper is what the wire is made out of. So now I'd have copper over here and over here, you see? So that would be a problem. So I have to connect it with something that will not actually take part in the reaction. Okay? All right, so let's look at this from this perspective. Again, you don't need to copy in those reactions because you already have them up here, I hope, right? But let's look at it here. I said there was one more thing I wanted to talk to you about here. You don't have this picture. It's okay. It's the same exact picture, but I've got, it shows you what's going on here. The copper is getting bigger. And that's what look at that electrode. That's what it'll look like over time if I left it run. And look at what happens to the zinc electrode, which, as Holden asked, well, how long will that last? Obviously not forever. Eventually you'll run out of zinc. And you'll run out, in this case, you'll run out of copper +2 ions. Okay? And that's when the battery is dead. Okay, now rechargeable batteries force a current back the opposite way and make this stuff plate back out onto the electrode. But you can only do it so many times. You can't recharge the battery forever. All right, what was I going to say? Oh, yeah, the last thing I told you was most confusing about this. The thing, and all of this is kind of, you can hear me even when I'm trying to talk about my two-potato clock. It's confusing for a lot of reasons. Here comes, if you weren't confused yet, you will be now. All right? The charge of the anode and the cathode. Look back. Look back to your electrolytic cells. What do you know the anode is charged in the electrolytic cell? What does it say? Look back there. Yeah. What's the anode in this case? Negative. This is so annoying. And it's weird, but I'm going to try to explain it to you. The reason these guys are opposite is that what you're dealing with here, watch this. This thing right here corresponds simply to this right here. That is a voltaic cell. This whole thing is an electrolytic cell. So when you're looking at this, you're looking inside the battery. Inside the battery, okay? Let's look what happens. Inside the battery, at the anode, where oxidation is happening, electrons are being produced, and they're traveling up that wire. Now let's take a look at the next one. Electrons are being produced and traveling from the anode to the cathode, where those electrons are being used to do reduction. So this inside the battery, you had oxidation going on. Out here, those electrons which were produced and come down here are used to make a reduction happen. And that's why, since the definition of a cathode or an anode is based on whether it's oxidation or reduction, the charges are not the same. Because the charge over here is the same, but the names of what's going on, oxidation or reduction, is different. All right, so it is confusing. I realize that. But the key to understanding this is your voltaic cell. This is your look inside of a voltaic cell, right there. That's what's going on right there. I'm sorry, not right there. Right there. All right, that's what's going on inside of that. Okay, the whole thing here is the electrolytic cell, and that's why it's confusing about which is positive, which is negative. All right, but there are things that don't change. The cathode is always going to be where reduction happens. The anode is always going to be where oxidation happens. And you know what oxidation and reduction look like as far as what's happening with their equation. So you should, even if you do mix up the positives and negatives, you should at least get partial credit. Because every one of these things is going to be partial credit on a test. If you label it correctly, you're going to have to label, is it electrolytic or voltaic? That's a point. Is it the anode or the cathode? That's a point. Positive or negative? That's a point. Oxidation or reduction? That's a point. The reaction itself? That's probably more than a point. You have to remember to balance it as well. All right, so all of that stuff is kind of important. All right, now your homework is right there. There's only 3 problems. They're not ABCs either. Copy those down, and that is it.